So we've looked at some non-renewable sources that have all been derived from the sun. They included coal and oil and gas, and they also included wood and biomass. Now we're going to look at some renewable sources that are derived from the sun. The first is solar energy. The way that solar energy works is we start with mirrors and we focus all of the sun's radiation into a single point. That focused radiation can be used to generate heat or to generate electricity or to power a generator. So, for example, sometimes all of those sun rays get shined on a tube that contains water, and that tube heats the water, which you could then use for, your shower or washing your dishes or so forth. Other times, we shine those mirrors, we aim them toward solar panels, and those solar panels produce electricity. So we'll look at some of these options. Now, this solar energy is really only a viable option for countries that have lots of sunlight. So, my Irish roots probably wouldn't do so well with solar energy because they have so many days that are cloudy, overcast, days of rain. Hydroelectric power is another type of renewable energy source which is derived from the sun. So the way this works is the sun heats seawater. That water becomes vapor, and it could be ocean water or it could be water in lakes. And that water becomes vapor. It condenses into clouds. Those condensed particles, a water vapor, actually they gather some dust and other things which causes them to fall down as rain, and those raindrops at the very top before they've fallen have really high gravitational potential energy. So when they fall, they'll hit well, sometimes they work their way down to the ground again in the form of rivers or waterfalls, and that type of flow of water can be used to turn a turbine. In fact, this is the very basis for the basis for hydroelectric power plants. So we start with these raindrops, which have high potential energy, and as they fall down to a state of zero potential energy, they run through a turbine. They spin that turbine, which spins the magnet of a generator, and that produces electricity. Now there's also wind power. Right? Wind power. So in addition to having this useful rain, the sun also heats up. Not only does it heat those water particles, but it also heats up the particles in the atmosphere. Right? It heats the air, and that causes air to become less dense because it spreads out when it's heated. As the temperature increases, the volume increases. And so those less dense air particles move upward, and that upward motion combined with the Earth's rotation produces winds. So wind can be used, it can be captured, it has kinetic energy, and those moving air particles can be used to turn a turbine and produce electricity. Now, in addition to wind power, there's also wave power, because the wind itself, some of that kinetic energy of wind, is given to the waves, to water, as kinetic energy. That water starts moving forward, and the water has now some new kinetic energy, which we can harness as well. The waves can be used to power turbines and produce electricity. In addition, we have some renewable sources that are not derived from the sun. So the ones we just saw were renewable and derived from the sun. Here are some that are renewable but not derived from the sun. The first is tidal power. Right? So there's this funny phenomenon, which we'll discuss more in class, and there's a picture that I have to show you, which we'll draw together in class. But the phenomenon is this. If you go to a beach, right? If you stand there at the beach at around, noon, the water level will be really low. And then if you go back to the very same beach around, say, let's see, what would it be? Say around 6 p.m., the water will be really, really high. So the water level changes as the Earth rotates, and this is caused by the gravitational pull of the moon. So we can get these notes down. We're going to discuss this in greater detail with the aid of a diagram, and we'll write that diagram into our notes. These tides, the high and the low tides, the changing in the level of water, is produced because of the separation of distance between the ocean surface and the ocean floor. And there's really only a noticeable difference between the ocean surface and the ocean floor and the moon when we're directly facing the moon or directly on the opposite side of the Earth from the moon. So when the moon is right overhead or on the opposite side of the Earth from us, that's when there's a noticeable difference between these distances. Okay, and we'll see this in the diagram. And this produces kind of a bulge in the ocean. So there's a bulge in the height there. And as the Earth rotates, that bulge travels around the Earth. So we'll see this in the picture. And that movement of tides can be used to drive, you guessed it, turbines and produce electricity. Lastly, there's geothermal energy, and this is really neat. We've all seen geysers, right? Pictures of big geysers, which are basically little, springs of water at the surface of the Earth, which have like a little opening at the bottom, and every now and then, giant spouts of water go flying up, shooting out of the opening in that little spring. And the water coming out is really, really hot. There's some gas, some vapor as well. Here's how that's produced. The Earth's crust naturally moves against itself, and it rubs against, the different layers will rub against each other, producing friction and heat, and that heat produces some really, really hot rocks in the crust of the Earth. Whenever water flows over those hot rocks, the water becomes steam, and in fact, it travels upward and achieves these really explosive speeds, which could then be used to drive turbines. Now we saw that this brief history of energy usage, and we did some practice problems. Now what we're going to do is take a quick look at coal engines, and we're going to talk about the evolution from coal engines to electricity. So a coal engine, when we look at like a steam train, right, what we see is that there's an external flame over this coal here, number one. So this is the firebox is what it's called. And number one, there's this coal which we burn with an external flame. That produces combustion fumes or exhaust, which travel upward into chamber 2, right? And it heats this water. This is a water reservoir. Now, the water gets heated, turns into steam. That steam is sent down into this piston, what's called a piston. And that water, the steam builds up right here, which pushes this piston to the right, causing these wheels to be turned by this rod here, this piece. So when this gets pushed to the right, these wheels turn around and they go counterclockwise in this picture. And then when they move down, that's caused by pushing of the right. That's caused by the piston being pushed to the right. When they move back around over the top of the wheel, when this rod moves over the top of the wheel, the piston moves back to the left and the exhaust is sent out through the chimney. So the important point here, an external flame is used. In 1852, this all changed. A method was developed that allowed for oil to be refined into kerosene, which has a higher energy density than coal. Kerosene could be injected inside of an engine and combusted using just a little spark inside of that engine. And so the combustion was happening inside of the engine rather than burning the coal way outside of the piston, right? We burn the coal here, which is really far away from the engine, the piston, this piston. What they learned how to do is inject fuel straight into the piston, combust it inside of the piston, and use that to move the piston. And this is called an internal combustion engine, what they developed, which operated on kerosene, which could be combusted inside, internal to the engine. That's an internal combustion engine. Now, these internal combustion engines, they were preferred because they used fuel with a higher energy density, but they were also twice as efficient as coal engines because they didn't have all that extra transfer of heat. In this thing, right? In this type of engine, you have to transfer the heat from here into the water, then from the water through the pipe and into the piston. And with these internal combustion engines, you had that combustion occurring directly inside the piston chamber, and that made it a much more efficient engine. So this new fuel, the oil, was also more easily transported than coal. Right? Coal had to be carried by trains. Oil could be pumped across large distances using pipes, which we now call oil pipelines. Um, there is a downside to oil. Oil spills, right? When oil is spilled, unlike coal, oil spills have disastrous environmental impacts. Now, a little bit later, in the late 1800s, electricity became an option. In 1831, Michael Faraday discovered how to make electricity from a moving wire inside of a magnetic field, and we've already seen now how that principle operates. We've seen the principles behind the operation of a generator. Then in 1866, and when Michael Faraday did this, it was not a very usable uh, generator. He couldn't produce a lot of electricity, and the electricity he produced was alternating current, which really they didn't have a use for. There was no known use for AC at the time. But in 1866, a man named Werner Siemens invented something called the dynamo, along with Charles Wheatstone as well. They invented the dynamo, and the dynamo was the first electrical generator capable of delivering a usable amount, a large amount of direct current. And this was a really powerful invention. It propelled the electrical industry forward. And then to add to this, in 1884, Sir Charles Pearson invented the steam turbine, which could be coupled along with the dynamo to drive larger generators and be used for even larger scale electricity production. Okay, so the last thing we're going to look at are a couple of different power stations. Here's a coal-fired power station. The first step, you burn some coal in a furnace. That furnace produces heat, and the heat boils water in a reservoir. Step 2, the steam that you get from the water is sent through a pipe toward a turbine. Step 3, the turbine rotates, causing a magnet to be turned, and this generates electricity. Step 4, the steam then is sent after passing through the turbine. It exits, and then step 5, it's sent into another section where it's cooled and it condenses back from steam into water. And then step 6, that water is reused in the next cycle and it's put back to the reservoir from step 1, gets boiled, and the process repeats. So here's a good schematic. We have our coal, it burns, there's a boiler. The coal produces these exhaust fumes, which travel upward, exhaust gases. They're really, really hot. They boil the water in this lower pipe. The water then rises as it becomes steam. The steam is directed toward a turbine, which rotates. It turns this big generator, and the generator produces electricity sent to your home. So the exhaust fumes from the boiler, right, they never actually contact the water, so the water never becomes contaminated. They just heat the water in the tubes, and then they exit this through the stack. Sometimes there are cleaners, scrubbers on the stack, but that was a development that was added as we learned about how environmentally impactful coal could be. Coal-fired power stations are not very efficient, only around 40 to 50%. Right? So not all of the coal's chemical energy is turned into electricity. Some of the heat from